G'day. Copy the heading down and then we'll do some hard yakka. We will start by testing your knowledge, so put down the numbers 1 to 10 under your heading. Question 1. What is the symbol for the metal mined in the Perborate region of Western Australia? Question 2. One way to calculate the valence of an element is to count the number of chlorines or hydrogens that the element combines with. So what is the valence of carbon in this chemical that we call methane? Question 3. What is the chemical symbol for the poisonous element mercury? Question 4. What precious metals have the chemical symbols Ag and Au? Question 5. The living cells of our bodies contain the salts of two metals with symbols Na and K. Name the two metals. Question 6. What is the period number, then the group number for magnesium? Question 7. What do we call elements that are brittle or gases and poor conductors of heat and electricity? Question 8. Which metal is used in electric wires? Question 9. What do we call elements that are in between metals and non-metals? Question 10. What metal is used to galvanise and protect iron? Pioneering Greek mathematician Pythagoras of Samos was a man of faith. He taught his followers that the universe was made up of simple whole numbers. In the case of the chemical elements, this is certainly true. Each element has its own particular whole number of protons. Boron is the lightest of the group 3 elements that we will study today. It is element number 5 in the periodic table and so has 5 protons. Notice that there are 2 isotope varieties of boron. They both have 5 protons. The fat boron isotope has 6 neutrons and the skinny boron isotope has 5 neutrons. Normally boron atoms are neutral, with 5 negative electrons exactly balancing the 5 positive protons in the nucleus. But the electrons can move around as boron reacts with other atoms. You will recall that the periodic table is divided into S, P, D and F block elements. The S block metals on the left are very reactive and form hydrogen and bases with water. Sometimes they explode. The D block transition metals in the middle are less reactive and are more likely to be used in pure metal form or as metal mixtures that we call alloys. Today we will look at the P block elements. Before we do that, copy these sentences and fill in the missing words. Previously, we have studied only metal elements. Now finally we have a wide variety of goodies in the one big box. The blue ones on the bottom left are metals. The yellow ones on the top right are non-metals. The white ones are the inert or noble gases. These noble elements just sit there in the universe taking up space. Are they metals? Are they non-metals? Who knows? They don't talk to anyone. Notice that there are elements in between the metals and non-metals in a rough diagonal line. We call them metalloids or semi-metals. Their properties are in between. Choosing which are metalloids in the periodic table is a tough call. All elements close to the metalloid line are a bit different. Take carbon for instance. It is an excellent brittle non-metal, as you will find if you bash diamonds with a hammer. But another crystal form of carbon, called graphite, is an excellent conductor of electricity. And that is a metal thing. As a second example, we could consider the element iodine. Iodine is part of the group 7 super nonmetals that we call the halogens. But just look at the crystal. It has all the appearance of a metal. Put a side heading for our first element, boron B. Boron shares a number of characteristics with its related elements in group 3. It has 3 electrons in its outer shell, and so its maximum and most common valence is 3. Having an almost half-complete outer shell, it is inclined to share its outer valence electrons with other elements rather than lose all 3. No group 3 elements are found free in nature, and they require lots of energy and clever technology to extract them from their compounds. But like many of the top elements in each group, boron is quite different from its relatives. It is the only metalloid in the group. It has a very high melting point of 2076 degrees Celsius, much higher than silicon at 1410 degrees Celsius. It is extremely hard at 9.3 on Mohs hardness scale, just under the hardest form of carbon, the allotrope diamond, with hardness 10. Like most metalloids, boron is a poor conductor of electricity. These qualities indicate that boron is forming tough networks of strongly bonded atoms in its crystals. One of the hottest, driest places on Earth is the famous Death Valley in California, where temperatures of 57 degrees Celsius have been recorded. It is a place where an ancient Pleistocene lake has evaporated, leaving behind a number of evaporite mineral deposits and poisonous small lakes, such as one called the Badwater. In the 1880s, a boron salt was discovered called borax. The overheated locals mined the stuff and took it out by mule trains. borax proved to have a range of useful chemical properties. It was mildly poisonous, but found uses in early soaps because of its ability to kill bacteria and fungi, as well as having a detergent action. Here we have a number of good folks extolling the virtues of borax soaps. Another useful chemical is the weak acid boric acid, which is made by reacting sulfuric acid with the salt borax. Its main use is as an antiseptic. It kills bacteria, yeast and fungal infections. So if you have bad acne, foot odour, athlete's foot and other nameless conditions, boric acid may be useful. It can also be used to cure hides, kill ants, termites, fire ants, fleas, silverfish and cockroaches. It is truly amazing stuff. Sodium perborate is another famous boron compound. It is still used for its mild bleaching action in a number of household cleaners and detergents. Being an old human, I can still remember the arrival in Aussie of the first household washing powder called Persil. It contained perborate and silica. Before that, we used Sunlight soap blocks in a metal cage. This was made in a factory in Balmain. Copy down this information for boron. Before we move on, I wish to outline the duty of good scientists to be sceptical about their research. Robert Boyle lived in the 1600s and is generally regarded as one of the pioneers of modern chemistry. One of his quality works was a book that he wrote called The Skeptical Chemist, where he challenged the scientists of the day to learn their chemistry by continuing investigation and experiment. Let us briefly look at boron compounds from the perspective of a skeptical chemist. After all, this disembodied old voice has called these chemicals truly amazing. Perhaps he needs challenging or even punishing. On first glance, boron compounds seem to be the most wonderful chemicals to splash around the environment. Having trouble with termites in your timbers? Just soak the woodwork in borax. Kids getting tinea in the change rooms? Regular use of borax in skin products would be wise. A really big environmental problem is the eutrophication of our waterways by the leaching and dumping of animal manures and phosphorus-rich detergents into our rivers, creeks and coastal areas. The waterways have become gardens for blue-green algae and the things that feed off them. Some of these little greenies can turn toxic and kill animals. The red tide of dinoflagellates is greatly feared and will kill lots of marine life. It has infected Botany Bay at times. Perborate detergents that lack phosphorus seem to be the ideal solution. Indeed, Australia's soils are some of the worst climate-blasted, mineral-deficient soils on the planet. Crops are often boron deficient, and may need a kilogram per hectare, or the crops will look something like this. But scientists have learnt to be cautious and keep doing useless research into side effects. It turns out that too much boron kills plants, and too much borax on the skin can produce nasty irritations, particularly in young children. It is a case of balance. A little is good, and a lot is harmful. Copy the next element heading, Aluminium. The solid outer layer of the Earth is called the lithosphere. The layer is brittle and has been cracked into a number of lithospheric plates by movements deeper within the Earth. The lithosphere looks like an eggshell that has been bashed around by a mad space kid with a spoon. Geologists divide the lithosphere into two layers. The lower layer is called the upper mantle. We humans see the dark-coloured rocks of this layer only rarely when they are carried to the surface by deep volcanic action. The top layer of the lithosphere is called the crust of the Earth. The Australian plate has two types of crust. The oceanic crust is thin, at only 5 to 10 kilometres thick. Black iron and magnesium-rich lavas are found there, with black basalt being common. The thicker continental crust under the Australian continent averages 38 kilometres thick. It is thickest under the Snowy Mountains and the Northern Territory at 56 kilometres deep. The dominant rock rich in silica and aluminium is granite, so the rocks are much lighter in colour. This old table gives you the rough percentages of elements in the Earth's crust. The two elements, silicon and oxygen, dominate the Earth's crust. And the next is aluminium. Oxygen is also an element of life. Silicon does play a minor role in the skeletons of some living things, whilst aluminium seems to have been rejected entirely as a component of living tissue. The other metals underneath are vital components of both plant and animal cells. Silicon and oxygen bond strongly together, forming silica tetrahedra, which have a similar structure to that of diamond. Silica tetrahedra are found in most of the mineral crystals that form the crust of the Earth, and they arrange themselves in all sorts of different ways. Generally, the silicate part of a mineral formula is negative and is balanced by fitting positive metal ions into the spaces near the silica frameworks. Let's look at some common aluminium mineral formulae. Notice that the silica part comes last. Even though silicon and aluminium are so abundant in the Earth's crust, the task of separating these elements from highly stable minerals remains difficult, hazardous, and requires a great deal of energy. The story of aluminium is very important for Australians. Meet the famous Danish physicist Hans Christian Ørsted, who is most celebrated for his experiments relating magnetism to electric currents. It seems that the good Hans was the first to produce aluminium metal by reacting aluminium chloride with potassium in 1825. I'm glad to say that he survived. Aluminium resisted all attempts to make it cheaply for 70 years. For the rest of that century, aluminium was more valuable than gold. In some hot areas of the world, rains can come crashing down and deeply weather the underlying rocks, washing away soluble elements and leaving behind insoluble iron and aluminium minerals. It has happened in Sydney during its wet geologic past, leaving behind hard laterite soils in parts of the Royal National Park. To the north of our continent, the hard, reddish, infertile, climate-blasted soils are richer in aluminium, and the laterites there are called bauxite. The useful chemical in bauxite is aluminium hydroxide, and this can be chemically processed into aluminium oxide, which is called alumina. Australia is a major world producer of alumina and its product, aluminium. Alumina is one of the Lord's toughest and most strongly bonded chemicals. Indeed, it has a precious hard variety called sapphire. It has an extreme melting point of 2054 degrees Celsius. You need an electric furnace to melt it, and further electricity to turn aluminium ions to molten aluminium metal. Oh, and the molten aluminium produced will react violently with any water present. The important breakthrough in extracting aluminium came with the discovery of a rare fluorine mineral called cryolite near Santa's hideout in Greenland. You mix cryolite with the alumina and it lowers the melting point dramatically. We can make the cryolite artificially from the pretty mineral fluorite. Problems remain with aluminium smelters. They use huge amounts of power to run and can emit fluorine gas, which is the most dangerous nonmetal in the periodic table. So aluminium plants need to be monitored by people of power and integrity, and the aluminium produced is best recycled to reduce world greenhouse gas emissions. It is easy to melt. Copy down these sentences about aluminium and fill in the gaps. As one of the world's most used metals, aluminium has some interesting properties. The first is that it is extremely reactive. Pure metal will react with water, forming hydrogen and hydroxide. The only reason aluminium metal survives is that its white rust coating is very hard and protects it. But that coating can be attacked. If you scrub aluminium saucepans with steel wool, the washing up water will quickly turn grey as the aluminium is exposed and reacts with the water. Mercury or any mercury salt touching aluminium will quickly corrode it. Alkalis are also a no-no, as they will attack it. Alkaline household cleaners such as strong ammonia or cement powder used by builders will corrode aluminium window frames. The British Navy discovered the problems with aluminium in its warships in its Falklands War with Argentina. Its ships were lightweight, but when hit with missiles, the aluminium burned. This flash gear offered little protection, and I will not show you the horribly burned sailors. Powdered aluminium is very reactive. This is thermite, a mixture of powdered aluminium and iron oxide. Here some dangerous fool has ignited it. It burns through a flower pot, a thick cast iron pot which melts at 1500 degrees centigrade, and then does nasty things to the back lawn. Rail workers sometimes use it to produce molten iron to weld damaged railway tracks. So copy this down and fill in the gaps. By far the biggest issue that Australians face with aluminium is the absolute need for effective recycling. Aluminium refineries require large generators burning fossil fuels to power them. Yet processing pure aluminium from scrap metal uses only 1/20th of the energy. There are effective recycling technologies, including eddy current separators, that school physicists may study in Year 12. Geology proves that many civilisations and fertile areas of the past have been destroyed by climate change. The fragile desert continent of Australia faces further crises, and we need to be the clever scientific country to face them. But enough of aluminium. What of the other metals of group 3? Gallium is one of the elements predicted by Dmitry Mendeleev, who called it aluminium. The metal is not common in nature and will melt in your hand and will dissolve into most metals and alter their properties quite dramatically. Uses for it may emerge in the future. Its compounds are used in some light-emitting diodes and may be of use in the quest for making cheap hydrogen fuel cells. Indium is also a rare low melting point metal. It finds some uses in liquid crystal displays, although some compounds are quite toxic. Thallium is an extremely toxic heavy metal that has caused terrible birth deformities in children in the past. It should be avoided like the plague.